Welcome back to the Deep Dive. We've got a great late-night vibe going on in the studio tonight, and we are jumping straight into something that I know keeps a lot of you software engineers up at night.
Yeah, it's a completely brutal problem.
It really is.
Yeah.
So just picture this scenario, right? You spend, I don't know, 3 weeks and maybe $20,000 fine-tuning this massive language model.
Oh, yeah. A huge investment of compute and time.
Exactly. You want it to perfectly understand your company's proprietary code base, and you deploy it, and at first, it works flawlessly. It's generating highly specific internal documentation. Everyone is happy.
Until the next day.
Right. The very next day, a junior developer asks it just a totally basic standard Python question, and the model outputs absolute gibberish.
Just total nonsense.
Yeah. By teaching it something new, you basically accidentally gave it complete amnesia.
And that is exactly what we're pulling from the LLM Mastery Series notes tonight. We are dissecting this specific phenomenon. Technically, it's known as catastrophic forgetting.
Catastrophic forgetting, just the name alone sounds intense.
I mean, it is. Because, as software engineers, you rely so heavily on the principle of building upon existing architecture. Like, you import a library, you write new functions, and your application just scales.
Yeah, adding a new data visualization module doesn't magically delete your user authentication module.
Right, exactly. But with large language models, adding new knowledge actively, and I mean frequently, destroys the old knowledge.
It just fundamentally defies all of our standard mental models for software development. It's like you finally master Rust borrow checking, and the second it clicks, you instantly lose the motor skills to walk.
That is a very accurate, if terrifying, analogy.
Well, tonight we are mapping out the literal anatomy of this bug, right? We're going to build out a defense in-depth strategy, and then later we're looking at this purely mathematical way to composite models that just bypasses the issue entirely.
So to start, the root of this amnesia, it actually lies in the physical mechanics of gradient descent during the fine-tuning process.
Okay, break that down for us. What's physically happening?
Well, when we take a pre-trained model and run a custom data set through it, the gradient updates are physically modifying the numerical weights across the neural network. The algorithm is basically calculating the fastest path to reduce the error rate on the new task, and it shifts the millions or, billions of parameters accordingly.
But the catch is, those specific weights already encode the pre-existing knowledge, right? From that massive initial pre-training phase.
Exactly. The fine-tuning algorithm doesn't, isolate the new knowledge. It just simply overwrites the parameters that previously held the nuance or the logic for the model's general intelligence.
So it's not setting aside a new folder for the new stuff?
No, not at all. The algorithm is entirely blind to historical context. It only evaluates the immediate local task.
Wow.
Yeah, and to understand why it has to overwrite rather than just add on, we have to look at the difference between traditional von Neumann computing architecture and dense vector spaces.
Okay, yeah, let's get into that, because I think that's where the mental model breaks for a lot of us.
Right, so in a standard von Neumann architecture, we allocate empty space for new information. You buy a larger hard drive, and you write new data to empty sectors using memory pointers.
The OS knows exactly where the free space is and just directs traffic there. Like, problem solved.
Exactly. But a neural network, once it's pre-trained, it has absolutely no empty space. It is a dense, fully saturated vector space.
Completely full.
Yeah. Every single parameter, every weight and bias is actively participating in the model's output. The network is completely stuffed with the representations it learned during pre-training.
So, pushing new information into a fully saturated space literally forces the old representations out.
Yes.
It's like, well, it operates a lot like a tightly coupled monolithic code base, but on this massive distributed scale.
Oh, that's a great way to put it.
Like, you tweak a function to fix a minor front-end bug.
Yeah.
And you completely distort the core back-end database logic because all the dependencies are just fully intertwined.
That's spot on, because a single weight might contribute, say, a fraction of a percent to parsing JSON, but it's also contributing to translating French.
Oh, wow. So they pull double duty.
Exactly. Pulling the thread to improve the JSON parsing inevitably distorts the French translation. And this collateral damage isn't a glitch in the code. It is a mathematical default of gradient descent in a saturated network.
So the weights update, the old representations degrade, and the model just forgets.
Yep. Which brings us to a huge problem. Relying on standard task metrics creates a massive, really dangerous blind spot for engineering teams.
Right, because if you're only looking at the new thing you taught it.
You're flying blind. An engineer might fine-tune a model to generate custom SQL queries, see a 99% success rate on their test set, push the model to production, and just completely miss the fact that the model can no longer format a basic JSON payload.
So if my task metric is showing a 99% success rate, I might just be wearing blinders to a burning building behind me.
Exactly. Optimizing for the local task at the expense of global intelligence is the single most common trap we see in enterprise AI pipelines. You focus intensely on the new feature and just assume the foundation is stable.
Which we just established it is definitely not stable.
Right. So the source material mandates this really strict evaluation protocol to detect the damage before you ever deploy. You have to run a broad benchmark evaluation suite both before and after fine-tuning.
We basically have to run a physical on the model, like check all its diverse cognitive domains.
Yes, a full physical.
And the sources mentioned some specific benchmarks for this, right? Like GSM-8K.
Yeah, GSM-8K is a great example. It stands for Grade School Math 8K. It tests multi-step logic.
So if it's acing the custom SQL test but suddenly failing middle school math, we know we've broken its underlying logical reasoning engine.
Exactly. If that score plummets, the model has literally lost its ability to think sequentially. And you couple that with tracking broad worldly knowledge using benchmarks like MMLU.
MMLU, massive multitask language understanding.
Right. It spans dozens of subjects: law, medicine, history. It acts as a barometer for the model's general understanding of the world.
And then I think the notes also mentioned HumanEval.
Yes, HumanEval is crucial. You run that to verify the general coding capabilities haven't regressed. Establishing this baseline delta is critical.
Because an improvement of 10% on the local SQL task means absolutely nothing if it's accompanied by a 30% drop across MMLU and HumanEval.
Exactly. You are literally quantifying the catastrophic forgetting.
Okay, so once we measure this degradation, the immediate engineering challenge is mitigation. How do we stop it?
Well, if altering the foundation inherently damages the structure, the most logical defense is to just stop altering the foundation.
Makes sense.
And that is the core philosophy behind LoRA, low-rank adaptation.
LoRA. I see this acronym everywhere right now. So this fundamentally shifts the architecture of the fine-tuning process itself.
It does. Standard fine-tuning updates the massive pre-trained model's original weights. LoRA locks those base weights into a strict read-only state.
Wait, so it freezes the foundation entirely?
Entirely frozen. Instead of modifying the frozen base, LoRA injects small, trainable adapter matrices into the network layers.
Okay, I see.
So during gradient descent, only the parameters inside these tiny adapter matrices receive updates. The original knowledge is preserved by construction.
Because the mathematical pathways of the base model are physically untouched.
Exactly.
So instead of tearing down the load-bearing walls of a house to add a new room, LoRA is like snapping on a lightweight modular extension.
That's exactly it. When an input passes through the model, it travels through the frozen base weights, retaining all that general intelligence, and is then slightly steered by the LoRA adapters to execute the specific new task.
So the overwritten gradients are contained entirely within the adapter.
Yes. And the real elegance of LoRA comes from the low-rank part of the acronym.
Right. What does that actually mean in practice?
It means it doesn't just add a massive new layer. It takes advantage of matrix decomposition. It represents the necessary weight updates by multiplying two lower dimensional matrices together.
Okay, so it's a math trick to save space.
A huge math trick. It reduces the number of trainable parameters by factors of 10,000 or more.
Wow.
10,000.
Yeah, it drastically lowers the compute footprint while keeping the main model completely safe.
That is incredible. We get a frozen base, a massive reduction in compute, and mathematical safety from forgetting.
That's powerful.
And here is where I play the skeptical engineer. The source notes emphasize a defense-in-depth strategy.
They do.
They list this whole arsenal of techniques: low learning rates, replay buffers, progressive fine-tuning, EWC. But if the base foundation is frozen and mathematically protected by LoRA, isn't stacking all these additional strategies just, over-engineering the pipeline for the sake of it?
It's a fair question. But we don't always have the luxury of using LoRA.
Oh, really? Why not?
Because highly complex domain adaptations, like, say, teaching a model an entirely new language from scratch or ingesting massive proprietary medical databases, they frequently require full fine-tuning to achieve the necessary performance. I see. So LoRA adapters just might not have enough parameter capacity to capture that level of fundamental domain shift.
Exactly. Sometimes you really do have to rebuild the foundation when the new addition is heavy enough. And Honestly, even when utilizing LoRA, the adapter itself can suffer from internal catastrophic forgetting if we train it sequentially on multiple new
Oof.
tasks.
Oh, the adapter weights will just override each other in the exact same way.
Exactly. So we need a toolkit to manage the gradient shock itself, and low learning rates are your first line of defense.
So just slowing down the updates.
Right. By forcing the gradient descent algorithm to take smaller steps, we minimize those violent rapid shifts in the parameter space that cause severe overwriting.
Just tapping the brakes on the gradient updates. What about replay buffers?
Replay buffers tackle the problem at the data distribution level. You mix in a small percentage of data from the old training set during the new fine-tuning process.
Ah, so it forces the model to continuously calculate gradients for both the old and new distributions simultaneously.
Exactly. It anchors the weights. The algorithm is forced to find a parameter configuration that minimizes the loss for both the new task and the historical tasks.
That makes total sense.
But you have to be careful. Managing replay buffers requires nuance. If you constantly replay the exact same 5 old examples, the model will just overfit.
It'll just memorize those 5 inputs and still forget the broader historical domain.
Right. You need a really diverse, representative subset of the original data.
Okay, and the notes also mention progressive fine-tuning.
Yeah, that follows a similar logic. You just slowly introduce new concepts over time rather than overwhelming the network in a single massive epoch.
So we ease the model into the new distribution.
Exactly. But honestly, the most conceptually fascinating tool in this whole arsenal is EWC, elastic weight consolidation.
EWC. Yeah, the note said it tackles the problem algorithmically.
It does, and it actually draws its inspiration from neuroscience, specifically how human brains manage continual learning.
Wait, really? Neuroscience?
Yeah. When we learn something new, synaptic consolidation protects the specific neural pathways that are most important for our existing memories.
That's wild.
EWC applies this biological concept to artificial neural networks.
So it mathematically identifies which specific weights were crucial for the previously learned tasks.
Exactly. And it does this by calculating the Fisher information matrix.
Okay, the Fisher information matrix. Let's not get bogged down in the calculus here, but what does that actually mean?
Fair enough. Basically, without doing the calculus, it measures how much the model's overall performance would degrade if a specific parameter were altered.
So if a weight has a high Fisher value, it means it is deeply critical to the model's historical knowledge.
Yes. EWC operates almost like a strict algorithmic pre-commit hook for the neural network's parameters.
Oh, I like that analogy.
If the new fine-tuning process attempts to alter one of those historically important weights, the ones with a high Fisher value EWC applies a mathematical penalty to the loss function.
So it literally increases the resistance on that specific parameter.
Exactly. It makes it harder to change. Meanwhile, the less critical weights, the ones with low Fisher values, are allowed to update freely to learn the new task.
While the fundamental pathways are locked down by mathematical resistance, that is brilliant.
It really is. And combining these strategies creates a highly resilient enterprise pipeline. Replay buffers supply data level protection, EWC enforces algorithmic protection, and LoRA provides architectural protection.
Defense in depth. We build a pipeline to manage the forgetting, but, the ultimate goal for AI engineering is seamless composability.
Oh, absolutely.
And the notes highlight this future paradigm called task arithmetic that moves entirely beyond defense. It shifts the focus to blending specialized models without any mutual interference.
Task arithmetic is incredible because it bypasses the gradient update problem entirely.
Okay, how does that work?
Well, imagine taking a base model and fine-tuning a copy to be highly proficient at Python. Then you take another copy of that same base model and fine-tune it separately for medical diagnosis.
Okay, so they are trained in complete isolation on completely separate compute instances.
Right. And because of that, they never experience the gradient collisions that cause forgetting.
So we're left with 2 separate specialized branches stemming from the same foundational tree.
Exactly. Now, here's where the arithmetic comes in. We take those branches and literally subtract the weights of the original base model from the weights of the fine-tuned models.
Wait, just straight up subtraction.
Just straight up subtraction. The result of this is called a task vector.
So it's a matrix representing purely the mathematical delta, like the exact weight differences, the literal isolated numbers required to learn Python or to learn medicine.
Exactly.
Hold on, this sounds exactly like a Git merge for neural networks, but using pure math.
That is exactly what it is. We take the Python task vector and the medical task vector, and we mathematically add them together.
Just adding them.
Yep. And we can scale and interpolate those vectors in the high-dimensional space.
So we might multiply the Python vector by, say, 0.5 and the medical vector by 0.8 to balance their influence.
Exactly. And then we apply that combined interpolated vector back to the base model.
We composite billions of floating point numbers to blend capabilities.
And the models never share a gradient update process, so the overwrite mechanism is completely circumvented.
The idea that we can do version control and feature branch merging on massive neural networks using basic linear algebra, that changes the entire collaborative workflow for enterprise teams.
It changes everything. But, managing model memory, whether it's through LoRA, EWC, or task vectors, it's a really complex, resource-intensive endeavor.
Yeah, fine-tuning introduces immense risk. It demands massive compute, and, as we've explored tonight, it continuously threatens the foundational intelligence of the model.
Which brings us to the ultimate question. The most crucial decision framework an engineer faces isn't how to fine-tune, but knowing when to avoid fine-tuning entirely.
Right, and we're going to map out the full comparison between prompting, RAG retrieval augmented generation, and fine-tuning in the next stage of this framework.
Because choosing the absolute right architectural tool before committing to the risks of physically altering the neural weights is paramount.
Absolutely.
So as you look at your own AI pipelines tomorrow, consider the trajectory of hardware and architecture. We spend this whole deep dive discussing how to protect the weights when injecting new knowledge. But as context windows grow to encompass millions of tokens...
Right, where you can just dump entire books into the prompt.
Exactly. Will the expensive, risky process of fine-tuning to inject knowledge eventually become obsolete entirely? Or will there always be a hard cognitive limit to what a neural network can deeply internalize simply by reading a massive prompt?
That is a fascinating question to leave off on. Are you teaching a new underlying behavior or just having it read a new document? Something to definitely mull over. Keep building, keep questioning, and we'll catch you on the next deep dive.